Okay, so now I want to talk to you about circular permutation. Circular permutation. Okay, so we saw what is a permutation. So a permutation is the arrangement of things. Permutation is the arrangement of things. So I gave an example where you have three bins, like the left bin, the middle bin, and the right bin, and you have to organize different shoes: blue shoes, red shoes, or green shoes. So blue shoes, red shoes, and green shoes. And you know, if you think about this, this is just the position of the shoes. It could be blue, it could be red and green, then it could be green, blue, and red, and so on. So you're kind of just shuffling. You're shuffling things. And we even saw that permutation is a special case of selection with replacement, without replacement, where the number of bins or positions is just equal to the things you have. So in the end of the day, because of that, you're just shuffling things, okay? So all the permutations of this situation would be blue, red, green, green, blue, red, blue, green, red, and green, red, blue, and then red, blue, green, and red, blue, green, blue, right? So these are the shuffling, the ways you can organize. Or you can even think about people. Let's say I want to take a picture, and I want to take a picture with three people: Louisa, Michael, and Brian. And you know, if I kind of call you guys to position yourselves for the picture, you could be, Louisa could come here, Michael here, Brian here, or you know, you could shuffle, because you have three positions, three bins, and three things without replacement to choose. Okay, so this is just a recap of permutation. Now let's talk about circular permutation. Okay, so circular permutation is this. Imagine that I have the same red, blue, and green, red, blue, and green shoe, and then I have to put them into a circular shelf. Okay, so here I have a shelf. Oh Jesus, I have a shelf here, and I have to kind of position, this is the circular shelf, and I have to position the shoe here, there. Okay, so you can think about this. I can position the red shoe here. Okay, I can position the red shoe, then the blue shoe, then the green shoe. Okay, this is one option. The other option, if you think about this, it could be, this is another option. It could be the blue shoe here, and the green, blue, and the green shoe here, and then the red shoe there. You know, but if you look, and you can keep going, but notice this: there's not a specific north, south, east, west, right? So you don't need to put like the shoe in the north and then the other ones in the east or west. You can put in the southeast, southwest, you know, like this, for example, this red shoe is positioned in a northeast kind of position, okay? So, or if you think about this shelf as having wheels, and you kind of you grab both sides. So here's your hand. You grab both sides of the cart, of the shelf, and just turn. So it's not the same as arranging things in a line. That's why it's called the permutation. The original one is called also as linear permutation. because, you know, if you change, if you kind of, things are one beside the other. Here, well, things are beside each other, but you still, you don't have a specific like angle to put it. So the way to think about is that is this. So imagine now a third option where you have the red one is here, then the blue one is here, and then the green one is here. Well, in the end of the day, although like the positions are like the coordinates are different, if you think about this is the same, right? So you have, if you think about the red boot is seeing a green boot to the left and is seeing a blue boot to the right. Exactly the same situation as in 1. So 3 is equal to 1 because the red boot sees a blue boot to the right and a green boot to the left. Okay, so although like this wheels kind of, if you turn, it will change the coordinate, the positioning is the same. Okay, it's the same thing as I'm saying, oh, Louisa, Michael, and Brian do a circle. But you know, if I kind of turn the circle, you're positioned in the same way. Okay. While you're in linear permutation, you don't shift things, you know, it's just one beside the other in kind of locus that are fixed. But here, you kind of you can kind of turn, and you're still positioned in seeing Brian to the right and seeing Michael to the left. So this could be equal to, let's see, L, M, and B. So I'm still seeing Brian to the left and Michael to the right. Okay. All right. So the circular permutation, when we're talking about linear permutation or the original permutation, we saw that linear permutations are like this. For the first layer of decision, or for your first bin, or for your first position, you have 3 options. For example, you can choose between L, M, or B. Then, because it's a selection without replacement, because you placed, let's say, L in the first position, you have only 2 options for the middle position, and then 1 option for the last position. So this is the 3 factorial, or 6 arrangements. Okay. Now, for the circular permutation, we have to kind of account for this. The reference now is not a fixed reference, but it can turn, right? The reference is the object itself. So the way to do it is, if you want to know the number of ways to arrange stuff, you have to first position one of the objects, right? After you position one of the objects, then you can decide who comes to the left and who comes to the right. Okay? If you don't have a position, initial position, you can't position objects, right? So if you're thinking about how to arrange 3 objects in a circular order, right? In a circular position, first of all, I have to position the red boot, for example, or the blue boot, or the green boot. So for the first position, I have actually only 1 option. Okay. Then let's say that I positioned my my red boot. Second position, let's say to the left. Let's say to the left, right? To the left, I have 2 options. I can put blue or red, blue or green. So I have 2 options. And then let's say I chose blue. Obviously, that the third position, which is the one to the right of the red boot, will have to be left with only 1 option. So in the circular permutation, I actually have 2 factorial. 2 factorial. And we can generalize this to any number of elements. So if we're organizing 3 elements, we will have 2 factorial. If we're organizing 4 elements in a circular shape, then it will have 3 factorial. In the end of the day, for circular factorial, you always have to discount the person or the element that sat or was positioned first. So for a circular permutation, the formula is not n factorial anymore as the linear permutation, but is actually n minus 1 factorial. Okay? Now, I will talk about a strategy you can use to solve problems that seem to be very difficult. And this strategy is called counting the opposite. Okay, it's a strategy, so it's part of our toolbox, and we are going to use it when things, when things are difficult to calculate, and we actually can think about not considering or considering what we don't want, right? So here's an example, okay? So again, if there are too many options, you're trying to calculate and break down the problem, it might be better to count the opposite, like count things that you don't want. So for example, this is the question: how many 6-digit PIN code use at least one digit multiple times? Okay, so let's break down this question. I have a 6-digit PIN code. So, well, I have 1, 2, 3, 4, 5, and 6. I have 6 digits. And this might be your door lock or something that you have to, you have to set up a pin. Okay. Now, this could be, for example, it could be a 1, 4, 6, 9, 8, 7. It is a valid pin. Because you're taking all the digits, right? You're taking the digits between 0 and 9, right? So it could be, for example, it could be 0, 0, 8, 3, 5, 1, okay? So it could be from digits, so the digits you're considering are from 0 to 9, okay? All right. Now the question is, how many of this 6-digit pins use at least one digit multiple times? So let's understand. I am actually not interested in this case, right? Because this don't uses pins digits repeatedly, okay? So this one is not what I'm talking about. Although it's a valid 6-digit pin, I want to know how many pins are, for example, this way. It could be 0, 0 because I'm repeating once the number 0. It could be 0, 0, 8, 3, 5, 1. But it also, this is something that I would be counting, but it also could be, let's say, it could be 2, 2, 2, 1, 8, 4, okay? This is also something of interest because I repeat one digit twice, at least multiple times, right? At least one digit multiple times. So the one digit 3 times. But I also can have, for example, I can have 4, 4, 2, 1, 1, 8. So I'm using at least one digit. So actually I'm using 2, 4 and 4, and 1 and 1 multiple times. So, you could try to think about finding this kinds of numbers, repeating numbers, you would have to, well, you would have to think about this. First, let's try to find the numbers that have 0 repeats, right? The 0 repeats, but you would have to kind of count of the one that repeats here, the one that repeats here, the one that repeats here, and then this is only the ones that repeat 2 times. You could have the one that repeats 3 times, and then you would have to organize and try to find, oh, how many repeat this way, or, you know, this way. It's undoable. It's unfeasible to count all of these things, and this is only for digit 0. You would have to go up until 9. Okay, so it's really try. I suggest you try just a little bit, like try to start. You'll see that it's very, very difficult. Okay, so when you have those situations, you have to think alternatively on how to solve the problem. Okay, so the thing is this: every other option other than the first one is what I want, right? So I want all of these options. Okay, I want all of these options. Oops, sorry. I want all of these options here, but I don't want the ones that that have single unique digits in each position. Okay, so if I can count, so from the total amount, think about this. If I think about the total amount of 6-digit pins, digit pins that I can make, if I subtract the total amount of pins that have unique digits, in each position, right? This is actually equal to the total amount of what I want, which are of pins that have at least one digit multiple times. Okay, so it's exactly this reasoning. You have everything, and everything is in yellow. This is, let's say that this represents, obviously this is a short list, but this represents all the pins. Okay, now if you take off this green part, if you take off this, right, and you kind of eliminate. So I want the opposite. I don't want the pins that have single digits in each position. Then you are left with what you want. Okay? So this is the reasoning that we're going to do. Okay, and how can I find the number of total 6-digit pins? Okay, so to find the total amount of 6-digit pins, you can go to our toolbox, everything that we've learned up until now, and think about, okay, so what tools did I have? I've learned about sets. Well, it's not actually a set. I learned about counting. I learned trees, okay, and I learned like trees, selection with replacement, selection without replacement. But I know that like these things, and the multiplication rule, these things are used to decisions. Okay, let me see if I can pose this question as a decision. I can, if I'm kind of in front of my door, inserting the pins, like setting up the pins, I would have to decide what number to put in the first position, or the first number, what digit that I could use for the second number, what digit I could use for the third number, fourth number, fifth number, and sixth number. So I can pose this problem as this. The total amount of six-digit pins is a selection. So this problem here is a selection with replacement problem. Because, well, I have six layers of decision with 10 options each one, right? Okay, with 10 options. 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So I have 10 options for each layer. And it is with replacement because, you know, if you chose 0 for your first digit, you can also choose 0 for your second digit, okay? So if you want to kind of work out this first problem, right, you would be doing a tree where you have 6 layers of decision, and each layer of decision has 9 options. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And then again, you would branch into 9 options again. So you would have a tree, and I'm going to draw it, it's too nasty, but you can reason with the tree. You have 6 layers of decision, or 6 positions of digits with 10 options. And we know that the selection without replacement, the selection with replacement, meaning that when I know that selection with replacement is that all layers have the same number of options. So I will have 10 options times 10 options for the second layer times 10 options for the third, for the fourth, for the fifth, and for the sixth, meaning this I have 10 to the 6 options. That's a million digits that I can, pins that I can form. Okay? So this represents my total amount. Now, think about this. What's the total amount of pins that have unique digits? Well, if you were to look at our toolbox, this is a selection without replacement. Why is that? Well, if you choose number 1 as your first digit, you can't choose it again because you don't want to repeat. You will have, so 1 will be used, and then in the second layer of decision, you won't have 10 digits anymore. You'll have 9, okay? So you can use for the unique digit, so this is for all pins, and this is for the unique digit pins. And what you're going to do is you will still have 6 layers. But you will have decreasing number of options. For example, in the first layer, you will have 9. Then in the second layer, you can't have 9. You will have 8. You'll have 10 digits. You have 10 digits, then 9, then 8, then 7, and then 6. And then 5, right? So you go up until 5. So first layer, second layer, third layer, fourth layer, sixth layer, fifth layer, sixth layer. And this, well, I did the calculation. This is 1 million. The calculation for this selection without replacement is 151,200 numbers, pins. And so the answer that I want, the answer is, well, the number of pins that I want is the total minus the thing I don't want. So it's a 1 million pin minus discounted these pins that are unique, giving me 848,800 pins. So again, you wouldn't ever find this by hand. I don't think even in the span of a lifetime you couldn't. Okay? So this strategy is named count the opposite. And this you can use this with all things that you learned. We learned trees, and the multiplication rules, which kind of it results in things like permutations, in things like selection without replacement, selection with replacement, circular permutation. It doesn't matter. Whatever counting technique you're using, you can always think, if it's too difficult and you know the thing that you don't want, you can always use count to the opposite. You count the total, then count the thing that you don't want, and just subtract. Okay? So now we're going to start a new concept named grouping or combinations. Talk about combination, or what we call grouping. And what is grouping? So grouping is when objects are selected, but we don't care about the order. Okay? So I don't care about the order I make a selection. I just really want to make a selection where I don't care about that. Okay, so let's say that I have 5 pair of shoes, right? And I need to select 2 of them to take to a trip, right? So let's say if I have a blue, green, a pink, a blue, a green, a pink, a red, a cyan shoe, right? So I don't care if I pick the blue one and then I pick the green, right? Or because this is the same as picking the green first and then picking the blue, right? This is a group. It's a group of 2 pairs, and whatever is inside, it's the same, right? It's the same. I don't care what I choose first. I don't care about the sequence of my actions. I just care about the result of my actions, right? So if I take to my trip the pink and the red, it doesn't matter if I took pink and then red or red and then pink, right? So we have to correct if we were to do a tree, right? We would say, okay, for the first bin in my luggage, in my suitcase, or in my backpack or whatever, I have 5 options, right? 1, 2, 3, 4, 5. I can pick blue, green, pink, red, and cyan. And then whatever option I made, for example, let's see, red, I can take 4 options, okay? Because I can take red again. So this is without replacement. I can then choose blue, green, pink, and cyan, right? So I have 5 options times 4 options would be 20, right? This would be 20 different choices, different paths, different sequences I could make. But this path here of picking up a red and a blue is actually the same thing. It's the same group of picking up the blue first, and then picking up the red. So if you were to pick up the blue, you could have an option of picking up the red, the green, the pink, and the cyan, right? So this is actually the same choice of that, right? So in the end of the day, if I do the tree, I am kind of overcounting. I'm kind of overcounting my possibilities. Okay? So I have to correct my multiplication rule when I'm talking about choosing stuff where the the sequence or the order does not matter. So I have to correct for my formula, for my multiplication rule, by understanding that I'm overcounting these instances of different sequences because I'm forming groups. So that's why it's called grouping. So let's see, my example here is I have this shoe, I have 1, 2, 3, 4, 5 shoe, and then I start stepping up, like I'm separating who's the shoes that are going to my luggage. They are here, right? So I put them aside. It could be the red and the yellow, or it could be the brown and the yellow. Then it could be the gray and the yellow. It could be the blue and the yellow, right? Or it could be the brown and the red. I don't need to pick the brown and the yellow because the brown and the yellow already appeared here, right? So then I will pick the gray and the red, the blue and the red. So I'm doing all the combinations. I'm combining all these things, the gray and the brown, the blue and the brown, and the blue and the gray. Okay, so that's what I'm doing. And again, if you were to do a tree, you would have you would have encountered a result of 20 possible sequences or right of choices. But because I'm grouping and I don't care about the sequence, I can actually, this is actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually I have 10 options, 10 different ways to group this different pair of shoes. And again, it doesn't matter if I pick the gray before and then the blue, or the blue then the gray. It just matters that blue and gray are together as a group. Okay, so here I listed every possibility. So I started the last one and the previous, the last and the so the last and the fourth, the last and the third, the last and the second, the last and the first. Then let's go to the red. The red already went to the last, already went together with the last. So red with the third, red with the second, red with the first. Then I'm gonna get the brown here. The brown already went with the red, already went with that one. So I start saying the brown with the second, the brown with the first, and finally I will take the gray. It went already with this one, with that one, and with that one, and I'll do just the gray with the first. Okay, so these are the possibilities. I did this by hand. You can try to practice, but it's clear to us that we will have to change the way we think about the choices. That doesn't matter the order. It doesn't matter the sequence of steps that I've made. So, and here we're going to define a new notation, right? To express ourselves. So for grouping. So if we write n, and it's this big brackets, so it's nk, n on the top and k here, it means that what is the number of ways? This symbol here, this notation here means the number of ways to select k objects from a set of n objects, right? So in our case, we had 5 objects, 5 pair of shoes, and I was selecting 2 objects from that. This notation is also known, it's also called the binomial notation. It's the binomial notation. And it means we can read this as 5 choose 2. So meaning that I have 5 options and I'm choosing 2 of them. A group, I'm grouping 5 objects in a group of 2. Okay, so 5, pick 2 or 5, choose 2. And the definition of this new notation is this. So this is n factorial over k factorial n minus k factorial. So let's work out our example. 5 factorial on the numerator, right, over 2, so k is 2, so it's 2 factorial here. Then n is 5 minus k, 2 factorial, okay? So if you work out the factorials, and this is fun to do, this is 5, right, factorial for 3 factorial, okay? This is 2 factorial, which is 2 times 3 factorial. These guys cancel out. You have 20 on the numerator over 2, which equals to 10. Exactly what we found by doing this thing by hand. Okay? So, it's good to know the formula, obviously. It's very useful to know the formula because we will need it. And it's just as you know some factorials by heart, like 4 factorial, 5 factorial, so they're easy factorials to make, to calculate, and because you've been doing some exercise, hopefully you're already familiar with it, so it's in your memory. It is very good as well to know some properties of binomials, right, or groupings. So first of all, if you have 0 elements and you're selecting a group of 0 elements, there's only one way of doing this, right? Remember that the binomial notation talks about the number of ways of doing something. So the number of ways of selecting 0 elements into a group of 0 elements is just don't do nothing. It's just 1, okay? The other property is whatever n you have, whatever number of objects you have, if you're selecting them in a group of 0 elements, right? This is also 1, meaning that there is only one way to choose 0 objects, right? Just don't choose any of them. Let's say if you have 5 pair of shoes and you're doing 5 choose 0, well, there's only one way. There's only one way of doing that. Just don't choose anyone. If you're doing n choose 1, it means that you're taking, for example, 5 objects and selecting them into groups of 1s. So, well, there are 5 different ways, right, to group your 5 shoes into groups of 1, right? Just choose one object. The other property is this, if you have n objects and you're selecting this n objects in a group of n objects. So it's like, oh, you have 5 pair of shoes and you want to select a group of 5 pair of shoes. Well, there's only one way to do this, and this is choose all the objects, choose all the shoes, okay? And finally, this is the most important property, and I want to really, I really want to highlight this, because this is actually the consequence of grouping. It's just a consequence of grouping. So let's use our example to understand what this means. So let's say that I have 5 pair of shoes and I'm grouping it into groups of a group of 2 elements, right? So I'm selecting 2 objects. So 5 choose 2 is equal to 5 choose 5 minus 2 right? So I'm gonna just, we know that 5 minus 2 is 3, right? So, and this is very important, because when you group 5 pairs of shoes, if you select, let's say within 5 pairs of shoes, if you select 2, you're naturally selecting 3, right? So if we go back a little bit on the previous slide, this is what's happening when you're choosing 2 pairs, right? When you're drawing this boundary here, here is what you're going to take in your trip. When you select a group that has 2 objects, you're actually drawing a boundary and separating another group that has 3 objects, right? So that's what that property tells us, is that the complement is being also grouped out, right? Again, you can have any configuration. If you draw this boundary here, and whatever is on the bottom is what you're taking to your trip, you're selecting these 2 objects here to go to the trip, and as a consequence, you're selecting 3 objects that are not going to the trip. So if you draw this line, you're actually selecting, you have 10 ways to select your 5 shoes to go to the trip, or in the same way, you're selecting 3 pairs of shoes to stay at your house. So that's what this property means. It means that if you're selecting 5 shoes, within 5 shoes, if you're selecting 2 to go to your trip, this is the same, it will be the same number of ways that you would be selecting within that 5, 3 to stay at home, right? So this is what this means. So this you can understand as a complement of the group you're making. So if you're taking 5 objects and combining them in a group of 2, or choosing 2, so 3 are, or the complement of 5, right? 5 minus 2, 3 are leaving, or actually being selected to another group, or they're being selected as well. Okay, so this is very important, and again, this is the binomial notation, and we can do several types of exercises. For example, you have a red ball, a green ball, and a blue ball, and you need to find the number of ways you can select 2 balls, right? So this is actually 3, choose 2. So within this 3, I need to choose 2. It doesn't matter if I chose red and then green, or green and then red. What I want is the group, right? So this is, when you're reading a problem, a question, this is very important to interpret what we're talking about, right? If you care about the group and not the sequence, you're talking about grouping. You're talking about binomial notation. If you're talking about sequences, and like picking red and green is different than green and red, then you're talking about a tree expansion, a pure tree expansion, and then you would use the multiplication rules or permutations, or whatever you're doing with your problem. But once you don't care about the sequence, then you will ultimately get into the binomial notation. Okay, so 3, choose 2. Well, we can work the formula out. So this is 3 factorial over 2 factorial, 3 minus 2 factorial. So if you work this out, this is 3 factorial sorry, this is 3 factorial times 2 factorial, 2 factorial here, and 1 factorial, which is 1. So this guy's get away. And so this is 3. This is the same answer. And if you want to check if you did everything right, just use the property of the complement. So the number of ways you can choose within 3 objects, the way you can choose 2 within 2 objects within 3 objects, so 3 choose 2 is equal to 3 choose 1, right? Because when you're selecting 2 objects, for example, if the green ball and the blue ball step up here, you're actually selecting within those 3. You're actually selecting a group of 1 object on the other line of the other side of the boundary. So, and again, by this property here, within 3 objects, if you need to pick 1, right, there are actually 3 ways you can choose, right? You can choose the red or the green or the blue. So it's exactly the same. So we checked that. Okay? All right. So now let's talk about problems where we need to mix the selections, right? We saw several types of selections with selections with selections with replacement, without replacement, and groupings, right? So now let's mix all the selections and groupings and things. Let's think about this problem. In a first clinical trial for depression, and just to be clear, a clinical trial is when you're in a professional health setup, right? So you're in a hospital or in a clinic, and a trial is an experimental thing, right? So they're doing a trial for a new treatment on depression, and the psychologists have 100 clients. All right, so they have a catalog of 100 clients, and they need to randomly select 10 clients to receive an experimental therapy with psilocybin, which is a new drug to treat depression. Okay, and the treatment consists of consuming the psilocybin and meditating, right? So they will consume the psilocybin, and they will be seated. Then they will be seated. We will put them seated in 10 chairs side by side, right? So the 10 participants will receive the medication, 7, 8, 9, and then they will sit in 10 different chairs, okay, that are side by side. In how many ways can my clients or the clients be selected and seated? So how many ways is it's possible to have different arrangements? Okay, so let's interpret the words here. First of all, I have a bucket of 100 clients, and I need to select 10, right? I need to select 10 clients. So let's think about it for a moment. If you have a bucket with 100 names, and you pick one, right? Let's say pick client A. You could first have set 100 options. So let's use numbers. Client 1, 2. So for a first selection, you have 100 options. Then, if you take, let's say, client number 1, You cannot pick the client again, so you will have 2, 3, 4 up until 100. So now you have 99 options, right? And then 98, then 97. But there's a problem here. Selecting patient 1, 2 or 2, 1 is the same, right? Selecting Louisa and Sabrina is the same thing as selecting Sabrina and Louisa. I don't care about the option. So I'm actually overcounting. So I cannot use just the selection without replacement, which is this tree that goes that decreases, right? What I need to do is I need to group people. What interests me is having a group of 10 people. So when I think about groups, right, in combinatorics, it means that we have to use the binomial notation. So what I want at first is 10. So 100, choose 10. So this is the combination of the number of different combinations of 10 people that I can make within 100 individuals, right? And we can work out the formula, and the formula is 100 factorial times 10 factorial over 100 minus 10 factorial. Okay. All right. So I take, I do the select. So this is not the way to go. But I selected 10 people. So I have 10 people, and now I have to arrange them in different chairs, right? I have to arrange them in different chairs. So this resembles, if you think about, this resembles me of permutation, right? Because they can be arranged linearly in different ways, okay? So then the formula for permutation is actually n factorial. So it's actually 10 factorial. And because I'm choosing, first I'm doing this decision, making this choice, and then this choice, I can use the multiplication rule. So it is true that my result will be first the combination or the grouping, right? And I have the number of choices. And because I will make a subsequent choice of how many ways I can permutate these people, I can actually multiply these possibilities, okay? I can actually multiply the possibilities. Again, permutation is a selection without replacement, okay? So first, for the first chair, I have 10 options. I choose a person. So for the next chair, I will have 9. I will have 8. I will have 7. I will have 6, 5, 4, 3, 2. I messed up something. Well, 2, 1. So this is 10 factorial. Okay. The difference between the selection without replacement and permutations is that permutations are the number of beans is just equal to the number of things you want to arrange, right? So a permutation is just having the 10 people like swapping positions, and the selection without replacement is generic. You could have like 4 chairs for 10 people, so then it would stop here, right? So permutation is a particular case of selection with replacement where you go up until 1, right? Okay, so this is the answer, okay? The clients, this is the answer, and well, this can get just this could get canceled with that. And this would be 100 factorial times 90 factorial, over 90 factorial. And well, you could work out this in, if you want to, and just see whatever you the result is. Okay. All right. Now, what I want to do is another kind of exercise. It's actually the same. It's actually the same task, but now I want to arrange the clients to be seated around a big table. So actually, in a second clinical trial, psychologists have 100 clients. Again, they need to randomly select 10 clients. So we already know that this is 100, choose 10, or within 100 people, I want to group people, 10 people. And then, so after I do this choice, these are the number of choices, then I have to make another choice, which is now this treatment consists of consuming psilocybin and talking. So they have to talk to each other. So the clients will be seated around a big table. So we will have 10 people here seated around the big table, right? And when I think about symmetries like this, I think about circular permutation, and we already know that to correct the formula for permutation to circular permutation, you can you just take the factorial formula and subtract 1. So this is 10 people minus 1 factorial, right? So this is 100 over 10 factorial, 9 over 90 factorial times 10 factorial. Oops, not 10, sorry, it's 10 minus 1, so this is 9 factorial, right? And, well, you could work this factorials out, okay? So this, well, we can always think of the problem and try to make. I always prefer to kind of reason on the problem, breaking the problem in different steps. So first I have a grouping, then I have a circular permutation or a linear permutation, and because I'm doing this choices in sequence, I can use the multiplication rule to multiply it. But this also can be lead us to new formulas, right? Mathematicians like that. So here we go. Selecting k objects from a set of n objects and then arranging this k objects linearly, right? So this is doing a linear permutation. If you work out this k here, if you expand the binomial part, this k will cancel this k, and we are left with this guy. Okay. And if you want to expand on the circular permutation, right, you would do, well, you select the group and then you you do a permutation in a circle. So you will take k minus 1 factorial, and if you work out, if you want to work out, you just, this guy will die with this guy, and you are left with this formula here. Okay? So these are our formulas that are worked out with the factorials. and you can check them if you want. Okay? All right. Now, let's talk about multiple groups. So let's unfold a little bit more this group practice, right? We know that when we group something, we group a number of k objects from n original objects. We are actually creating two separations, right? Just as the shoe, if you select two shoes to go to the trip, you are automatically selecting three groups to stay. But now let's say that I'm not only grouping shoes to go to a trip, I'm actually grouping shoes to go to a trip, shoes to donate, and shoes to clean, right? So I'm actually grouping and selecting objects into multiple groups, okay? So just to give another example and not continue with the shoe one, let's talk about this example here where a group of 12 people need to go to King's, right? They need to go to campus, and there are 3 cars available. You have a red Tesla that holds 3 people, a blue Toyota that holds 4 people, and a green Nissan that holds 5 people. And the question is, how many different ways can I choose to select and arrange these people in the cars? So how many ways can I select and arrange, right? So for example, I could have chosen this guy, and this guy to the Tesla, then this one, and this one to the Toyota. And in another particular way, so this one, and this one to the Nissan. So this is one particular way, right? This is one particular way that I can select and group the people and then put them into 3 bins, right? So I have to group the people and put them into 3 bins, okay? So I have to, and I'm going to write that. I have to group, because wording is good for us to understand the problem. I have to group people into one group of 3 people, one group of 3, one group of 4, and one group of 5. And then I will have to take these 3 groups and arrange them into the 3 bins. So I will have to permutate the groups, okay? And arrange or permutate into 3 cars. So this is the problem, okay? Now, when we think about multiple groups, we will introduce yet another notation, which is what we call a multinomial notation, okay? But before I introduce the notation, let me get rid of this arrows. And first of all, nothing. Let me get this right. So I will have to group the people, and then we'll permutate the options, right? Or permutate the number of choices that I have, and permutate the number of choices, not the groups, and permutate the number of choices, okay? All right, well, anyways, this problem has two parts. It has two parts. The first one, I have to group people, and then I will permutate. So let's focus on the first part, which is grouping. And let's then reason that. Now, first of all, I have to take 12 people and choose 3, right? This is the first thing that I have to do. Then I have like a number of different options or choices that I have here. Then, actually, after that, I will be left with 9 people, right? Because let's say this guy is out, this guy is out, this guy is out, okay? So I'm left with 9 people, and then I'll have to choose 4. So 9 choose 4. And again, I'm using the multiplication rule because this is subsequent choices. Then as subsequently, so I eliminate 4 people here, okay? And then I'm left with 4 people here, and then I'm left with this 5, which I will have to select 5, right? And it's compulsory. These are the ones that just, they're just the ones that that remained. Okay. So if you work out this binomials, you will have 12 factorial over 3 over 9, then 9 factorial over 4 factorial over 9 minus 4 factorial, which is 5, times 5 factorial over 5 factorial over 0 factorial, which is 1, right? So this guy goes away, this guy goes away with this one, and we're left with 12 factorial over 3 factorial, 4 factorial, 5 factorial, okay? So this is the result, or the number of ways I can select 12 people into groups of 3, groups of 4, and then groups of 5. Okay? So this is the first part of the problem, and we can, and then we will actually state this new notation, right? And this new notation is what we call the multinomial notation. Multinomial notation. The multinomial notation is then a notation where you have n objects, and you're first selecting a first group with k1 elements, then a second group with k2 elements, and how many groups you want, but they have different elements, so they have different sizes, right? And you have whatever number of groups you want, okay? So this notation is to describe exactly what we've done. So you have it's the subsequent choices of grouping different things, and this is what we have, right? So this is very important. First of all, obviously that this needs to hold. So for example, if you have the 12 people and you're dividing into a group of 3, then a 4, then a 5, obviously that 3 plus 4 plus 5 needs to sum up to 12, right? Because first you divide in 3, then in 4. Obviously you're left with compulsory 5 people. And this is just equal to, it doesn't matter the order, right? Because this is groupings. So it doesn't matter the order. If you choose 5, 3, and 4, This is actually the same. And just to be clear, the multinomial notation, you won't never find a multinomial notation with only 2 partitions. Like, well, first of all, you couldn't have 12, choose 5, choose 3, choose 6, because this is not summing up to 12. This doesn't exist. And the other thing that is not used, that doesn't exist, it's actually the notation of multinomial with 2 groupings. Like, let's say, let me give you an example of the shoes. 5 shoes grouped first 2 and then 3, right? It must be 3 because we have to sum up to 5. So what this means is I take 5 things and I make a first group with 2 elements. So I choose 2 and then I choose 3. Actually, this notation doesn't exist because this is actually the multinomial, right? We already know that if you have 5 and you choose 2, you're automatically choosing 3, right? So we just drop the second part and we use the binomial notation by itself, right? So usually you see multinomial notations when you have more than 3 groups. Okay? Okay, so that we can end our exercise, the last thing that I have to think about is, after grouping 12 people into a group of 3, a group of 4, and a group of 5, and actually what I'm counting here are the many possibilities I can do that, right? Actually, if you think about the people that were assigned to the Tesla, so three people were assigned to the Tesla, and if you think about the beans or the seats in the Tesla, you have the driver, the passenger, and then the back seat, like 3 bins. Imagine that this is 3 bins. So all the possibilities of 12 choose 3, all of them can actually be permutated. So let's say that one of the possibilities of 12 choose 3 is getting person A, person B, and person C in this configuration. But but the problem asks to group and arrange. So how many ways I can group and arrange? So actually this is different from making B, C, and A. So I can permutate 3 people into 3 bins. So let's say that you have 12 group 3, right? And this 12 group 3 gives me several possibilities, several number of ways, right? Each branch of each possibility will branch out into more possibilities as a permutation of the 3 bins, right? So how many ways can you permutate 3 people in 3 bins? It's actually 6. It's 3 factorial, right? 3 factorial. And again, I have this is a linear permutation. It's not symmetric, so you still have bin 1, 2, and 3 here. So after I grouped, I can multiply through the multiplication rule. So I group, then I permutate 3. So each branch will be I will multiply each possibility. This is the number of possibilities. Let's say 500. I'm just making this number up. Please bear this to mind that I'm making this number up. Let's say that's 500. Then I will branch this into 3 factorial, right? Because each of these possibilities will have the Tesla permutated, but also each of this possibility can have the Toyota permutated, so 4 factorial, times the Nissan permutated, 5 factorial. So this is the answer to these to the exercise that we've proposed. And again, the thing that you need to practice a lot is how to read the exercise and break it into smaller pieces, smaller subsequent actions, and really imagine what is going on if you were to draw like a tree. So the trees, they were useful for us to derive the multiplication and addition rules, but they're also useful to think about, like, if each possibility you could branch on 6 different possibilities for the Tesla. Then if, let's say that you pick one of the possibilities for the Tesla, then actually you will branch 4 factorial for the Toyota, right? And so on. So imagining the tree branching is a very good strategy. Okay? All right. So now let's talk about indistinguishability. So when we are grouping, it doesn't matter if we're doing one group or multiple groups. Again, one group means doing 2, so it's the binomial notation because of that. Once you group one part, you're actually leaving out the other, so it's a binomial. It's a bi-grouping, and multinomial is multi-grouping. But all the problems that we've did up until now is grouping into predetermined groups. For example, the Toyota group, the Tesla group, the Nissan group, or when we group on shoes, right? The shoes that is going to travel, the shoes that is staying home. Now, there is a very important distinction when we cannot tell the groups apart, right? So usually we can tell them apart. So, who is in team A? Who is going to the shoes that are going to the trip? The shoes that are staying home? Or what is going to the Toyota, to the Nissan? Or what is fruit? What is not fruit? What is Mrs. Leboni's class, or Mrs. Hikian class, right? Or so when you label the groups, it's very it's really using the binomial or multinomial notation, as we saw. But a phenomena happens when we can't identify these features, right? So you can't identify like the groups as team A, team B, and so on and so forth. And you must rely actually on a relative meaning of groups. And I'll give you an example, a practical example, so that we can understand that. And ultimately, we will have to correct our formula for groupings, for multinomial groupings, and even binomial groupings when we can't identify groups. So let's say that you have 4 people. So Alex, Brandon, Charles, and Daniel, and we need to make we need to group them into 2 groups of 2 people, right? So what we're doing is 4 choose 2, right? We're doing 4, choose 2. And if I do this 4, choose 2, I'm actually considering that, for example, and this is I worked out all the possible combinations that we can. If we are considering a label to the teams, so let's say that I'm considering this first column as team 1, team 1, and this one as team 2. And if team 1, if I do this, the binomial term actually solves this problem for me when I have a label, right? So when I have a label, this guy here, this guy here, Alex and Brandon, Charles and Daniel, is actually different from this group, right? It's actually different because A, B are in team 1, and C and D are in team 2, while in this arrangement it's on the other way around. Okay, but when I don't have a label for the teams, I just say, look, I just want to group two groups of 2 people, right? It doesn't matter, like this A, B go to one side and CD goes to another. It's just equals to CD to this line, right? If you think about this people being on a classroom, if AB goes to the left and CD goes to the right, it's exactly the same grouping as CD goes to the right and AB goes to the left, right? So because there's not a label to each group, you just want to separate. So I usually call indistinguishability as separation. So indistinguishability as, it's not a grouping, but it's a separation, right? And when we have these kinds of problems, we actually, if we apply the binomial or multinomial operation, we will be actually overcounting, right? We will be overcounting. So in the end of the day, to know if you're doing a separation or not, you have to ask yourself if the group has a name, or if you identify your group by a relative perspective. So being in that group. For example, if I'm Alex here and I look to my partner, I see that it's Brandon, and it doesn't matter where in the classroom I am, if I'm on the left wall or in the right wall, this is the same group, right? The same thing is if Daniel looks to his partner and he sees Charles, and okay, it's the same, it's exactly the same group. I'm not telling them that they are in team 1 or team 2. I'm just separating them. So when we have separation, we have to ultimately correct our formulas. And so if we take this example, right, I'm just going to eliminate this guy because it's the same from that. I'm going to eliminate this guy because because it's equal to the second line. And finally, I'm going to eliminate this guy because it's the same as the third. So actually, 4 choose 2 would have a result of 6, but actually our answer is actually divided by 2. So our answer is actually 3, right? So how can I modify? I have 1, 2, 3, so it's actually 3. How can I modify this formula to make this guy, to work out this guy, right? And you can actually practice with more setups to derive the formula, but I'm just going to give you the solution here, that the workaround that we need to do is this. So here it is. I just copied it. And what we do is for a collection of k groups that are indistinguishable, we divide by k factorial. So if we're doing 4, choose 2, and both of these groups are indistinguishable, then we will divide by 2 factorial, right? So this will be exactly the result that we have, okay? So let's do another example, and I'm going to use a multinomial notation. Let's say that we have 17 elements partitioned into subsets of 4, 4, 3, 3, and 3 elements. Right, so we know already the multinomial notation. We have 17 separated into 4, a group of 4, another group of 4, then a group of 3, then a group of 3, and another group of 3. Right, so this is what we're doing. So first, I'm separating 70 people into 4, then the 13 people that are left, I will separate again into 4, and then the 9 people that are left, I'll separate it into 3, and then 6 into 3, and then the compulsory last one, 3 into 3. All right. And if we work out as if this problem is totally labeled, right? So let's say let's work this out as if this first group of 4, it's group. So we have 4, 4, 3, 3, 3. So let's say that this is A, B, C, D, and E, and I'm making this up, right? Because I don't need to. I'm just separating them. I'm not grouping. Well, actually, I am grouping, but I'm not grouping it with labels. I usually call this a separation. So it is clear that obviously that I can tell that this group here, 4, this first group of 4 is different from the group of 3, right? We can. So imagine people inside a classroom. You ask them to divide themselves into groups of 4 and 3. It is obvious that you can tell them apart, right? You can distinguish them, although they don't have a label, right? So this is just makeup. This is just made up. Although they don't have a label, you can actually distinguish between the group of 4 and the group of 3, right? Just by analyzing the number of people. So you can tell them apart, although you don't have a label, right? You can imagine that because of this difference in number of elements, it is as if there's a natural label in it. You can look at it and you will see the difference, okay? But at the same time, the 2 groups of 4, they're indistinguishable between them, right? So between the group of 4, if you imagine the classroom, and you have this 4, 4, 3, 3, 3, but if you swap positions, like if this groups of 4, it's not team of 4A or team of 4B. It's just they're just teams of 4. It's indistinguishable, right? So you have 2 indistinguishable groups for this collection, right? You have 2 indistinguishable groups for this collection, and you have also an indistinguishable group 3 indistinguishable groups for this collection here, for a collection of 3 groups, right? Again, I don't have team of 3A, team of 3B, team of 3C. It doesn't matter, you know, if person, 3 of the persons are in the left most of the room, in the middle or in the right. It doesn't matter. The groups they're indistinguishable, okay? Because they don't have any kind of characteristic, qualitative characteristics that can distinguish them. Now, between 4 and 3, of course, yes, I can, right? Distinguish, because there is a qualitative characteristics that you know, that you can tell people apart. Well, this person is in the group of 4 and not in the group of 3. Okay, so there are different groups. So what the theory tells us is, for each collection of k groups that are indistinguishable, so for each collection we divide. So work out the multinomial as if everything was distinguishable, right? So 17, 4, 4, 3, 3, 3. But then divide for the first collection, for every collection. So I'm dividing for the first collection by k factorial. So this first collection is 2 factorial. And also we'll divide by 3 factorial. So this is the answer. Right, so you work out as these groups were separated, right? But we know we're overcounting, right? We're overcounting in this group. Inside the groups of 4, we're overcounting. Inside these groups of 3, we are overcounting. And for this first collection, I have an overcounting in 2 groups. And for the second collection, I have an overcounting for 3 groups, so I just divide them by 2 factorial and 3 factorial. Okay? Cool. So I am pleased to tell you that we have ended the combinatorics parts of the course, or the counting part, and it's just it. It's just this. It's a few, there's a few concepts that you need to know: the addition rule, multiplication rule, the selection with replacement and without replacement, permutation, which is just a specific case of selection with without replacement, circular permutation as well, then combinations or grouping, which we use the binomial notation, multiple groups, which we use the multinomial notation, and indistinguishability. So if you know what you're doing when I'm telling you all these items, if you know what they mean and the concepts, you are good to go with combinatorics, and that's it.